已经有 WhatsApp 都加入那个网络了。
下了，还没有加入。
有多少人加了？谁加？都没加啊。Ah, it's already works. Okay. Sounds good. Okay. Okay, thank you. Thank you very much. So we come to the third lecture of the relativistic density function. So essentially, in last lecture, we completed the introduction of the relativistic density function and also the framework. And since this framework or this formula are so important, therefore I would like to repeat it again in simplified way so that you got the idea what is the relativistic density function. And also I found maybe it's much better to change the strategy of my lecture. And at the beginning, I plan to cover all the application of the relativistic density function. But then I realized that as you may see at some point, I edited a book about 700 pages. So that means if we want to cover the full application, maybe we need 1 month or even more. Therefore, I decided to choose only topic to prove to you that is how powerful the relativistic density function. And then we have some extra time. How to use that extra time is very important. And in China, we always have WeChat, right? WeChat. So everybody join this WeChat, and then we have a cycle of the participants. I noticed that some of you have also downloaded or the software is WhatsApp, right? So perhaps you can help me a little bit. Everybody, after these 4 lectures on the relativistic density function, everybody writes and lists 2 questions because we have 40 of them. So maybe putting together, we have 80 questions. 80 questions. From this 80 questions, maybe you remove some double counting. Then underneath, we could have maybe underneath 20 interesting questions. And then under this 20 questions, in the last lecture, maybe we go through this question one by one. I definitely cannot answer all these 20 questions, but we can discuss underneath in such a way that we can stimulate. Some of these questions may lead to Wittgenstein discovery or important work. So who is the chair of this workshop? So did all of you join in or not yet? Then maybe you do that. Or somebody could initialize to join this so that you can send all these questions to this WhatsApp, and then combine this 80 questions together. Finally, we have remove the abundant one. Then we have around something like 20 questions for Friday afternoon. Okay. Are you okay with this idea? Yeah. 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 Okay. You are the chair of this. Okay, then maybe you collecting all this question, and then finally we have 20 questions, and if everything discussed already, then maybe on Friday I will give you some special talk on the relativity density functional, which I suppose is very fancy, but the experimentalist might not like this idea. But anyhow, that I will let see. That is my planning for Friday. So okay, we go back to the relativistic density functional, the starting point, right? So from the history point of view, at the very beginning, everybody studied from sigma model, right? There is this in the field theory, there is famous number 4 theorem, how to build up a coupling or a Lagrangian for the scalar field. So in relativistic mean field, everything studied by coupling this scalar meson with the nucleus, right? So later on, Valachka introduced this omega meson in such a way that we take into account the important part, the attractive part and repulsive part. Putting this together, then of course, there are also a lot of efforts in including other mesons, like null meson, delta meson, pi meson, and so on. But I should tell you that in this sense, the relativistic density functional is phenomenological. Of course, you can put as many meson as you like, but the less number of the meson, the better. Because only when you prove that is necessary, then you introduce more mesons, right? And then when you're letting out this meson, you see this part. If you have a free nucleus, this part is the Lagrangian for the free nucleus. And this part is the interaction of the nucleus, which describes the nucleus. To make it simple, we forgot about the other mesons. We only concentrated on the sigma mesons. So this is the simplest coupling for the scalar mesons, right? And then for this part, this is the Lagrangian for the scalar mesons. And then once you see, okay, we build up the Lagrangian for the free nuclear and the free mesons, and then we added that coupling here. That is the Lagrangian for sigma mesons. And then, of course, in Valachka model, which is also called sigma omega model, because you including sigma meson and omega mesons. Then you do the same thing, right? You do the same thing by including the coupling with sigma omega meson and also the free part of the omega mesons. Then you can continue this business, If you do a little bit more job, there are always some efforts to say, okay, for example, if you study the equation of states, then normally the relativistic density functional, if you describe the nuclear structure well, they always tend to be soft to describe the equation of state for neutron star. Then people say, okay, why don't I include it? Maybe that is signal for missing some important mesons. Then I put in more mesons to see whether the equation will become stiffer. So this is, you can always have this freedom. Underneath, you can try that, How could you know that maybe at some point it might works? And then from this Lagrangian, of course, you might have this Hamiltonians. And then have this Hamiltonian, you see you formulate the Hamiltonian in such a way that you have a kinetic part, that's a T, the interaction part, right? But the interaction part that composed out of the, different meson contributed to the different vortex, right? And then, of course, if you quantize the field, then immediately you end up with two-body interaction. Then with the two-body interaction, you are, you are free to do whatever. For example, in previous lecture, Professor Nicolas Schenk has already told you, how to formulate a Hartree-Fock, how to formulate a Hartree-Fock-Bogdubov. And what he mentioned is fully agree. I just added a little bit of my thinking about this idea, right? So the mean field means every particle or the system could be treated as a set of independent particles. If you remember even in our high school study physics, we treat ideal gas. What is ideal gas? Ideal gas means the gas molecule move independently, no interaction between them. That's very simple. The same idea is also true when we want to study the nuclear physics, nuclears. Why don't we treat each nuclear independently? This idea works, right? That's why Mayer and Jensen got the Nobel Prize. You introduce a potential and you assume the particle move independently within the given potential, it works. Then comes, if you, so to say, for example, if we also have the interaction between the nucleons, then our idea is that why don't we have a way to transform this system into a special potential? This special potential we don't know. How can we find this special potential? By Hartree-Fock approximation. After we did the Hartree-Fock approximation, wonderful. The nuclear system could be treated as one nucleon after the other, right? That works so well. And then, as mentioned in the previous lecture, what about open shear nuclear? If the shear is not closed, for the nuclear between two magic nuclears, the shear is not filled up. So we have to consider pending correlation. Pending correlation is terrible because two-body interaction and then makes things more complicated. Then again, we want to have quasi-particle. Quasi-particle. The idea of quasi-particle is again the same. We want to treat the system composed out of also independent particle. But after you include pending correlation, this idea of independent particle doesn't work anymore. So we have to introduce quasi-particle, right? So we treat the system as a kind of system of non-interacting quasi-particle. That's the idea of Hartree-Fock-Bogdubov. If you do a transformation by algebra, you see we don't know. We don't know how to do that. But underneath the starting point, we know. We have a Hamiltonian with two-body interaction. The goal we want to achieve is that we want to transform this Hamiltonian into a system which composes out of only independent quasi-particles, so that the property of the system could be described well for quasi-particles. So this is the same is true if you have this two-body interaction. Finally, you did some approximation, then you build up the density function now, and then you have this equation of motion, right? You have this equation of motion. And this equation of motion, of course, as I mentioned, this is Dirac equation. But if you forget about the vector potential and the scalar potential, then this is a free Dirac equation. And this free Dirac equation, we already know from the textbook how to solve that. And then, of course, add up the vector potential and scalar potential. If you forget about how complicated they are formulated, it's not that difficult. And then, of course, for the meson, I have Klein-Gordon equation. But for the Klein-Gordon equation, we can do that by so-called point coupling approximation. Then we can remove this part. Yes. Okay, you see, this is scalar potential, and this is vector potential. Yeah. You see, this the difference. The psi is the so-called the Dirac spinner, right? And this is the psi bar times psi that give us the scalar potential. And this psi star and psi give us the vector potential. Yeah, the law B, sorry, this law B exactly corresponded to the law V. This is because the vector potential is essentially the Bayesian density we are talking about non-relativistically. Therefore, that we also put that, and sometimes we also mixed this vector potential and the Bayesian densities. The vector density and the Bayesian density is essentially the same. And then this is third components of the potential, because we have the isospin, the third component of isospin here, which is important to calculate the so-called for the normal mesons. And this is the charge density, which should be important when we want to calculate understand the charge densities, right? So, oh yeah, sorry, this is very important. And at this point, you see, in principle, that in this, when we sum up the calculation of all this density, we should sum up from negative infinity to the Fermi level. But this is definitely the result where diverges. Therefore, we normally calculate the density in such a way that we cut off to the Dirac sea. That means the Dirac sea is frozen. When during this calculation, we assume the Dirac sea doesn't exist. Therefore, this is also called a no-sea approximation. So somehow that in the calculation of this coupled equation, we use two assumptions. One assumption is that we adopted the no-sea approximation. That means when we calculated all of this density and the currents, the summation doesn't including the contribution from Dirac sea. That's a yes. Tau 3 is the isospin matrix. Yeah, you see that because in this system, isospin is a good quantity, right? So we don't mix the proton and neutron. This tau 3 is simply an expression we calculated only, for example, the contribution for the isospin difference. I wonder whether I make it clear or yeah, thanks. And then this is a no-sea approximation. That means we neglect this part Yes. That means the proton density distribution. That's when we want to calculate the charge density. Yeah. Yeah. Another approximation adopted here is the mean field approximation. The mean field approximation means that we studied from some initial potential for this VR and SR. Then we repeat, we solve this equation, we get the wave function. After we get the wave function, we calculate these densities. From this density, we solve the Meson field. From this Meson field, we build up the vector and scalar potential. Then we go back to the Dirac equation, and we repeat this process, so-called iteration. Finally, until between two iterations, the scalar potential and the vector potential we put here is the same as the vector and potential we finally calculated. Then we see this equation is self-consistently solved. So the keywords here is we adopted no-cell approximation, we adopted mean field approximation, and then this equation of motion are solved self-consistently. And all the density functional theory here, for example, when we solve these equations, we have to adopt some symmetry. Well, we can allow not all the symmetry to be broken. For example, the spherical symmetry, axial symmetry, and the deflection symmetry, and so on. We can break all of this symmetry. Or we can assume the system to be spherical symmetric. Then, of course, if we assume the system is spherical, this equation is reduced by adopting this spherical symmetry. You solve this system, all the solution will be spherical. If you don't adopt any symmetry, then the system simply found the minimum, right? After you get the minimum, all kind of deformation are possible. So therefore, we see, okay, for all the deformation and rotation and pain energy, this equation are solved on the same footing, right? And then again, for this bond company, if the Meson mass is too heavy, is big compared with kinetic energy, we can expand it in such a way. And then finally, we can have we can only have to solve this Dirac equation. Yes. Good question. That if the mass number is big enough, then by the expanding that go to the high order, we can guarantee their convergent. And then you are fully right that there is no exact provement of this, justification of this approximation. The only thing is that, okay, it works, then we're fine. Yeah. And another way is that, for example, instead of this nonlinear expansion, we can adopt the density dependence. Then the density dependence may be taken into account what kind of this correlation. That's another way. Yeah. Okay, so then putting this together, that we have to only solve this equation. Then, as I mentioned, we have all of these parameters which need to be decided. I simply mentioned here, this is Dirac equation, and this is the parameter we need. And then just choose PCPK1 functional. That means point coupling PK1 functional. This is, later on I will introduce you, this is only one of the most successful functional or analyst. So far, it applied, so, it's achieved very, very good progress in describing all the nuclear phenomena. And how to get this functional? We simply choose, 60 easy proton magic or neutron magic nuclear mass. That means the bending energy are taken into account for the fitting. And also take something like a 20 charge ready as a constraint to constrain this around 10 parameters. So remember, all of this nuclear either proton magic or neutron magic. That means all this nuclear are spherical. And then part of this ready are also used as constraint. After we got these coefficients, these coefficients are supposed to be used for all the nuclei in the nuclear chart. And we also should use this functional for neutron star, for nuclear matter. And then the question comes, the describing of this bending energy and charge ready, this is simply from fitting. But for the other property, it could be regarded as a kind of prediction, right? Then we will see how good it will go. And then after we solve the Dirac equation, this is the important formula to calculate the bending energies. Then another question comes. Do you know what is the center of mass correction? Because, for example, if you do quark model, you assume a nucleon is composed of 3 quarks. You also have to take into account this called center of mass correction, because we assumed all the motion of the nucleon is with respect to the center of the mass. In such a way, we break in the transformation invariance. So we introduce some spurious motion for the system. Therefore, that's why we should take into account the center of mass correction. Once you introduce the center of mass framework, then you have to take into account this center of mass correction. And the Penn energy is very important. Of course, Penn energy is also very important. And then for the deformed case, because we broken the rotational invariance, so we also have to treat, we have also take into account the so-called the rotational correction. And then we can calculate the nuclear radius. By the way, the radius we're talking about is always root mean square radius. We always take that for granted. Someday, one student asked me, why do we calculate the root mean square radius? Right? The reason is because if we simply calculate the average radius, it will be values, right? So the simple way is go to the second order, then we calculate the square of the radius, the average value. And then when we're talking about the radius, what we're talking about is always the root mean square radius, right? And again, you can calculate the charge radius and so on. We can also, for deformed nuclear, then we can also calculate the so-called the quadrupole moment. We can calculate all kind of moments and then see how it could be done, right? Like nowadays, for example, in particle physics, for the investigation of the CP variation, they may be interested in understand what is the dipole moment. And then essentially can be calculated because we have a single particle level, we have everything. And so far, in such a way, we assume this relativistic density functional theory is self-consistent and macroscopic. It means apart from this functional, the parameter in the functional, then for the nuclear property, essentially we should, so to say, from the solution, we try to provide everything. Yeah. Like including the amount of inertia and so on. But for that, we normally use English formula without penning case, or the barrier formula, English barrier formula, if we thinking about the pen correlation. Okay, so then essentially this part is done. And then I suppose we should go to the second part. The second part is, as you may know, that nuclear physics is in some sense computational nuclear theory. Most of our time is is working for the computation. Therefore, that I would like to also introduce a little bit the numerical sense. Okay, for the numerical sense, and I suppose you already got an email about this code for nuclear matter and spherical nucleus. So I would like to invite Yao Cheng Yang. He is the youngest participant of this school. Maybe he introduced to you how he has learned how to solve this Dirac equation for the nuclear matter and the spherical nucleus. That's maybe perhaps we should encourage him as the youngest participants to contribute something for the school. Yeah.
And this code is written by my group, and I'm just here for introduction. As as you may know, I'm just a young student, so you can relieve yourself. It's beyond my power to instruct something too difficult, and my instruction will be brief and direct. Okay. Okay. And during my introduction, if you see something inappropriate, do please point out. And you have any question, do please ask. And if my answer is not so satisfied, I do hope someone could help me to answer it. Anyway, I will start. So the most important thing is that we want to have a single Newton equation that is so if you have a single Newton equation, you can solve the wave function, and if you have the wave function, you can have property that you want. So in fact, if we get this, then everything is done. But you know, just to solve this equation may be very difficult. But if you look into some specific system, you may have specific system, and this symmetry may make you make the things simple. So here we introduce two specific system, which is one is nuclear matter, and then the other one is the spherical nuclear. And the last thing is that the single nucleon equation we often hear is not like the form of Schrodinger equation, it's the Dirac equation. So if you're not familiar with this, maybe we can give a brief introduction of the Dirac equation. But this introduction may be very simple and just give us a feeling of what we are doing. So let's start our first part, the free particle Dirac equation. So first, we think about the Schrodinger equation. How we get the Schrodinger equation? We start with the non-relativistic relation, which is E equals to P squared over 2M, and then make the substitution E equals to RH bar partial T, and then P equals to minus RH bar blah. And let both sides act on a wave function. We get the Schrodinger equation like this. And we can see this Schrodinger equation is of first order in time, but second order in space. So it doesn't satisfy the Lorentz invariance. If we want to construct an equation that satisfies Lorentz equation, we should let the order of time and the space the same. So a very natural thinking is that okay, we keep the equation to be of first order in time, and keep the space of first order in time too, and then we can construct an equation that is of first order in time and space. It's like this. And similar to the Schrodinger equation, we should let the coefficient alpha and beta to be determined, that is by satisfying the relativistic energy momentum relation. And then this equation is called the free particle Dirac equation. And now we have to determine the coefficient alpha and beta. To obtain the explicit form of alpha and beta, we compare the equation with the relativistic energy momentum relation, that is like this. And then compare this and this, we can have the relation that the alpha square equals to beta square equals to 1, and the alpha I times alpha j plus alpha j times alpha I equals to 0, and then the other one. And according to this equation, we know that the alpha and the beta we want is not just a single number. It should be a matrix. And it can prove that the lowest dimension of this matrix should be 4. So Dirac suppose that, okay, we just choose the minimal equation dimension that is 4. Then we can get the form of alpha and beta like this. It's a form dimension matrix where the sigma is the Pauling matrix and the I is the 2 plus 2 unit matrix. And we have get the Dirac equation at now. Maybe I should write it down. Like since we have the free particle Dirac equation, we can solve this. and it's not a difficult task. And I give a quick introduction. Like first, the expression could be spanned in the momentum representation that is like this form, and the UP should satisfy. We substitute into the origin equation, and then we can get this equation. And then we write the four components final U in terms of this, and then we can express the direct equation like this. And then we can get the solution like this. Is yes. Okay, so it's a very brief introduction of the Dirac equation. So we see that it's a free particle Dirac equation. So if you want to solve the nuclear Dirac equation, we should have some potential. That's effort that the energy density function will do. Anyway, we will get something like we just put some potential in this. We may have some vector and scalar field and the things like this. So you see, the difference is that this is no longer a free particle Dirac equation. So we should have some potential. The potential may be vector or maybe scalar. So from the energy density functional, we can know what the explicit form of the potential, and through some procedure we can get this like this one, which is I should write this. And the vector potential. So if we get the single Euclidean equation, then I have said that everything have done, because you know the form of the potential, and you can solve this equation, and you will get the wave function, and then you can through the wave function to get the property of the nuclear. The other thing is that we have to notice that the potential is dependent on density. And the density is dependent on wave function. So you will find this equation solve a little difficult because everything is tangled with each other. So we need a iteration process like this. First, you may have some initialization, like you can give an initial potential. From the initial potential, you will get a Dirac equation, and then you can solve the single particle states. Through the single particle state, you can have the density, and through the density, you can again get new potentials. You use the new potential to solve the Dirac equation again. Then you get new potentials. You throw this iteration until the potential are converges. Then you can get the final answer you want. Okay, that's the 1 and 2 parts of my instruction. Is there any questions? Okay. Now, we can solve this equation, but if we look into some specific system, we may have some specific symmetry, which can help us to simplify this solution. Like if we solve this equation in the nuclear matter, we see that for nuclear matter, it should have the time reversal invariance, which suggests that the space component of J and V should be equals to 0. And due to its uniformness, which we also can say the translation invariance, the Laplace rho S and the Laplace JI mu should equals to 0. And through these two symmetry, we can simplify the S and the V like I have write like this. And another thing is that when you look at a nuclear matter, you have to know what's the density of the nuclear matter. That is, for nuclear matter, you know it's the neutron number density plus proton number density, and you also know its proton number density minus its neutron number density. And you will find that this property and this property, this one is equals to J subscript 0, and then this one is equals to this one. So for specific nuclear matter, you have known the J0 and the J03, which implies that the V0 you have already know. So you don't have to don't need iteration to solve the V0. All you have to solve is this S vector. So I may write a circle like this. J you have no. The thing you have iteration is rho S. So rho S you can calculate S from this sentence. And now if we have S, how can we calculate psi? And that's the PowerPoint. So since the nuclear matter has the symmetry of translation invariance, you can say the momentum P is a good quantum number. So we can express the function in the momentum representation, that is UK in this form. And through this form, you can use this form to substitute to this equation, and you will get the single nuclear direct equation like this. I have put the V into the P and the V0 into the E. So you will find that this equation is very similar like the free particle direct equation. So we will get an analytical solution like this. So we have the psi K. And so we have already know the brief procedure of how we calculate this equation in the nuclear matter. We have know the only intuition we need to do is S, and how we calculate the direct equation psi K is it has an analytical solution. And through psi K, we can have rho S, and rho S we can get another S. That's it's a very simple case of how to solve this solution. And then we can have some properties of nuclear matter, like this. This is the energy per nucleon, and this is the incompressibility, and this is the symmetry energy coefficient. Okay, then we will get the program. So you see this, if you just solve the nuclear matter, the whole thing is not so difficult because the most difficult one may be psychic, but it have a analytical solution. So the program the code is somehow small too. First, of course you have to use a make command to compile the program. Then the executable file is called this one, SNM. When you use the SNM, he will need you to input a baryon number. The baryon number is equals to neutron number density plus proton number density. And to specify a nuclear matter, you need to input an asymmetry too. The asymmetry is something equals to you put a proton number density minus neutron number densities. So this example is we put the baryon number density equals to 0.154 and put the asymmetry equals to 0. And we will quickly get a output like this. This is the baryon number, and this is the energy per nucleon, and this is the incompressibility, and this is the symmetry energy. And that's the code of the nuclear matter. Is there any problem? Okay. Oh, sorry. Thank you. Now we come to the case of spherical nuclear. For spherical nuclear, it may be a little difficult. First, we may also see our potential. You see, first, we also have the time reversal invariance. So the space component of J and V should equals to 0. Also, in spherical nuclear, due to its rotation symmetry, the potentials only depend on radii r. Thus, we can write our potential like this. You see, it's rather complex. So at this time, the S and the V subscript 0 should both need to be solved by interaction. Then what about if we know the potential? What about to solve the wave function per psi k? We know that if we are doing something in Schrödinger equation, and it is rotation symmetry, we may express it in the spherical harmonic basis, and we may write the solution like something like this. And we already have known this is the harmonic, is a spherical harmonic function, and the only thing we have to solve is this radial function, and it's the same in the Dirac equation. Since it is a rotation symmetry, the total angular momentum J, the Z component of the angular momentum, the orbit angular momentum, and the spin are good quantum numbers. So we can express the psi r in the form like this, just something like we do in the Schrodinger equation. And then the only thing we have to calculate is the radial function, and the remaining radial wave function should satisfy the equations below. And to solve this equation, we may notice that it may not have an analytical solution. So we should solve this equation numerically. And this is one thing that now we should solve this thing numerically. And the other thing is that we notice that the L and J could be infinite, but we can't solve all the J and M. So a lucky thing is that now we are compute the ground state. So maybe we just solve some lower J and L and M, and then we can cover what we want. So we have introduced how to calculate psi k, and then through psi k we can calculate rho s the J0. It's not a difficult one, and through the density to the potential we have discussed in the in the above papers, then we will come to the code. You see, this code is rather complex compared to the nuclear matter. But if you just use it, it's also simple. First, you also have to use the make command to compile this codes. Then they are no longer that you run the executable file and he let you input some inputs. Now we write an input to let you to choose some inputs you need, because in this case the inputs may be more. Then you have modified the inputs, then you can use the run command to run the executable file. When the file is end, and then you can extract the information from the output files. So if you just want to calculate some spherical nuclei, the thing you have to focus on is the executable file run, and the input file dir dat, and the output file dir out. So what is it like in the input dir dat? Let me show you. If you open the inputs dir dat, you will find something like this. The first six lines is something that we have examined, and you cannot it's appropriate that you just use this number. So if you just want to calculate some nuclei, you may just change the nuclei you want to calculate. But maybe it's appropriate to give some introduction of this parameter. First is the R max, the bulk size of R box. That is, when you calculate a nuclei, maybe you want a binary condition, a binary condition. That is, in this point, you let the psi equal to 0, and when you calculate it from the 0 point and a very long point, and you have to let this point equal to 0 in this point. And the next is the X step. The step size is easy to understand, because when you solve a differential equation, you always need something like this. then this one is the maximal number of iterations. And this is a mixing parameter. And this is the initialization of potentials. If we choose 1, then it is the Wuzhen-Saxon potentials. This is a initialization of the levels. Then this one is what we always to change. For this example, I will show you the output of the oxygen 16. And this one is the pairing. I haven't introduced the pairing in this sense, but if you want to calculate some open shell nuclear, if you want to get a more accurate output, maybe you should add some pairing. You may use the empirical equation like this, but it's just a empirical equation. And let's see this. This is the maximum number of levels. That is, I have said that we can't solve all the L and M, so we just solve something of this, and then we have to examine that these things can cover what we want. And the first line shows the J, and the N or P present the neutron or proton. Plus or minus shows positive or negative shows the spin is 1/2 or -1/2, and the N max is the main quantum number of N, and the number is that you solve the 14 of N, and the more you don't solve. That's the input file. And the output files, first, it will show you the input and the initialization. After this, he will start to iterations. Through the iterations, he will show you every step of iteration, the output like particle number, lambda, delta, and so on. And when the iteration ends, he will have this output show that the iteration is end. And then when the iterations end, first he will show you the mean field potentials. It is written in the function of R. Next, he will show you the density distribution of the function of R. Then he will show you the single particle he has solved. Finally, he will show you some property we may truly interested in, like the particle number, the R, the charge R, the total energy, and the energy per nuclear. That's the introduction of the spherical nuclear. Is there any questions? Yes. And this is an example of the ground state properties of oxygen 16. The functional we use is a PCPQ1, and this is some numerical details. And we will get the ground state property like this. This is the bound energy, and this is a neutron ready, this is a proton ready, and this is a charge ready. You may run this yourself, and you will find this suitable to the experimental data. You see the angular momentum cutoff. Yes, you can lower it, but in principle, you have to examine. That is, when you use a cutoff like this, you have properties. Then you have to show that when you increase the cutoff, the property no longer change or it converges. Then you can show that the cutoff is enough. But in this case, the cutoff is surely enough, and it's easy that we not change anything, just the nucleus. Yes. Yes. There are any questions? Yes. 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 It's all the same potential, all the same function, all the same potential, and all the same parameters you may have seen. Yeah, you may have seen this. It's all the same, and it's yes, it's all the same. So it's also an advantage of this functional.
Since even more simple, I also prepared something which you might find it very helpful. So what I put it here is so-called the numerical details. As I mentioned that essentially after we fix the density function, after you fix the coefficients, then you assume this coefficients is from first principle, you cannot touch anything. Of course, in the future, we should study from some first principle to calculate these coefficients. Nowadays, it's still fixed by the data. But once you fix that, you cannot change it. Then the most simple way is that we apply that for nuclear matter. For nuclear matter, this is purely theoretical Toyer model because nothing could be observed for the nuclear matter for experimentalists. But it's wonderful because nuclear matter, in principle, all the model you could apply that. You apply to describe the nuclear matter. And then let me see what is ideal nuclear matter. Nuclear matter means number one, we should neglecting the Coulomb field. If we don't neglecting the Coulomb field, this system will immediately collapse, right? So for nuclear matter, the Coulomb field is neglected. And secondly, you see, is infinite, it's uniform. That is nuclear matter. So if it's infinite and it's uniform, that means for the nuclear matter, all the Bayer function, all the wave function for the proton and the neutron should be the eigenfunction of the protons. So proton, should be the eigen wave function of the momentum. That means momentum is a good quantum number, right? And then you know that all the source all the source currents are independent of the spatial coordinate. Otherwise, the system is not uniform. So immediately, then you can simplify this, the equation of motion immediately reduce to a kind of algebra equation, not differential equation, as just mentioned by Yao-Chen Yang. Then solve this algebra equation. That is what we have learned in high school. So immediately we can we can solve this equation. Solve this equation, then definitely we should calculate, for example, the energy and the pressure. Then we can plot in the energy and the pressure as a kind of equation of states. And then just show you an example. For example, you see this is the saturation point of the nuclear matter. So this is some of this wave function, which, as I mentioned before, that this is a kind of nonlinear density function. This DDME1 is because it's too soft. So when you go to some high density, about 2 times of saturation density, then you will find that there is a minimum here. This minimum, in my opinion, is due to some numerical fitting. We cannot fix this value there, right? Remember that in all the density functional, because we use the property of finite nuclear to constrain the functional. Because all the information we put in is below the saturation density. Therefore, everything beyond the saturation is a kind of prediction. You cannot really trust that too much. But one thing, as I mentioned, for example, you see, for example, just as I mentioned that this PK1, you see this line here, they are not fitted for nuclear matter, but it's well seated, will pass through this saturation point. So the saturation point described quite well. That's how we see, so to say, okay, we're happy with this functional, because underneath we can test it for nuclear matter and it works well. And then there are also a lot of properties for nuclear matter. People are talking about symmetry energy, for example, when you're talking about equation of state, the important thing is symmetry energy. But this symmetry energy is really too complicated, and most of the time we extract that for finite system, right? Then the symmetry energy is defined in such a way. We also talking about the incompressibility. Incompressibility nowadays, from experimental, how to extract that, more or less model dependent. Yeah. But I mean, how gradually the people try to reduce the uncertainty and then try to get the symmetry energy and incompressibility. This is from nuclear matter, how we can get this informations. And then, so this from the density functional, we can see, for example, this is empirical value. This empirical value is, so to say, for example, you study from liquid drop, you go to infinity, then you get this bending. This is the bending energy per nuclear. This is the density, and this is effective mass, and then what kind of symmetry, energy, and incompressibility. I just show you, I just highlight here this PCPK one you see, because at the beginning I emphasized it's not fitted for the nuclear matter, simply doubly magic nuclear. Then you will say, okay, works quite well. That's the reason why we can trust this function. Yeah. By the way, after you construct a functional, then the important thing is that you try to use that for different prediction and make sure it works. If it doesn't work, then we need a new function, right? So that is the way we develop. And most importantly, you see this figure is a little bit complicated because then Sagawa tried to put, this data was, this figure was first drawn by Hiro Sagawa. And then he used the data from Wumishkak. He see, okay, this is the T0 and T tau, the incompressibility. And then this is from all kind of models. You see key tau is I just show here. You see this is the incompressibility, right? This compressibility is defined in such a way. So you see, this is how this incompressibility is defined, right? And then from this incompressibility, if you go here, this is so to say this is so to, that is called the volume term or the surface part. And then you can see this is from the combinatoric experimental value. This is so-called empirical values. And then this is a prediction from all kind of model. You can immediately calculate this. Then you will see this is several of this functional which survive because finally they agree with that data. In such a way, then okay, you can also apply that for neutron star. When you using the neutron star, the important thing is that you should take into account the chemical equilibrium, right? Then because how to make the neutron and proton balanced. And then that is the conclusion for the finite for the nuclear matter. If you go to finite nuclear, then it's a little bit of complicated. Why nuclear physics is so difficult? Because we have boundary condition, right? Nuclear matter is uniform, but nuclear has finite size. This finite size always comes with the surface, with a boundary. This boundary condition is very difficult to treat. Therefore, I just listed that in nuclear theory, what has been done, right? There are kind of algorithm recipes. First of all, we could do that in coordinate space. In coordinate space, it's much more complicated, but still we can do. As I mentioned on the history of the relativistic mean field, when the people try to solve this deformed Leon 20, they did use this different approach. And then in coordinate space, another way is the harmonic oscillator basis. Harmonic oscillator basis, when we study quantum mechanics, the harmonic oscillator is a classical example. One-dimensional harmonic oscillator, three-dimensional harmonic oscillator, and then their solution is analytic. And then the composite are combinated basis. Use harmonic oscillator basis, we can diagnose all kind of Hamiltonian simply by matrix diagonalization. What we need to do is calculate the matrix elements. Matrix diagonalization, you can have standard procedure. And then recently, there is also Wu-Saxon basis. Wu-Saxon basis is not that popular. Why? Because the solution is numerical. Numerical is not so simple to handle. But there is cases. For example, if you want to treat the halonucleus, harmonic oscillator always have the potential going with the, when you go far away from the center, the potential will go up. Going up means that we're constrained the nuclear size. So it's not useful for high nuclear. But the harmonic for the Wu-Saxon potential is very useful because it has a natural boundary condition. And then this is for bound state. If for unbound state, like we're talking about the high nuclear, that means we have a continuum. Then we have to develop a different approach to treat this continuum. For example, we need to get that resonance energy, we want to get that shift. So there's a scattering phase shift approach, magnetic continuation in the coupling constant, the box discretization method, and so on. So all of this approach has been used to investigate the continuums. And then for the finite nuclear, in coordinate space, so far we have solved the spherical, deformed, or even all kind. This is not the present case. In the present case, we can fully solve the equation of motion in 3D lattice. So everything is possible. And then in harmonic oscillator basis, so all kind of, for example, spherical, deformed, traction, reflection, and symmetry has been done. And then for Wu-Saxon basis stabilization, this money orientated for treated hollow nuclear. So far, it's spherical nuclear, actually deformed, traction deformed. This code is already available. And then this is for the continuum. This is scattering phase shift, magnetic continuation, box discretization approach. Anyhow, if you are interested in continuum or resonance, this kind of approach is kind of standard. One should also learn from that. Then maybe Yao Chen has already introduced you a little bit. So when we want to treat the equation of motion for spherical nuclear, next day maybe Nicola already told you, for example, what is the initial condition, what's the equation of motion. The equation of motion, if you adopt the symmetry for the equation of motion, that is constrain the path, during the iteration is always on the track. And the initial condition, you can always take whatever you want. But then, for example, if we want to treat the nuclear, the simplest way is that we assume the nuclear is spherical, right? We cannot prove this nuclear are not really spherical. That time we have experimentally, if you say, okay, this nuclear cannot rotating, there could be only vibrating. That could be a single note of spherical. But anyhow, spherical symmetry is much simpler to treat theoretically. So theoreticians like spherical symmetry very much because it makes the things very easy. Then for spherical nuclear, the Dirac spinor wave function could be written like this. This is a little bit strange, right? It's nothing special because if you derive the Dirac equation, first of all, you have up components, and then you have no components. And then if you have a spherical symmetry, you can separate the radial part and angular part. This is the isospin part, distinguish the proton and neutron, so you can forget about that. And then after you get the radial equation, well, you found that if we formulate, if we divide the wave function by 1/r, and then we have put some coefficients here, this equation will be much simpler, right? So there is nothing special that the Dirac equation should be writing, or the Dirac spinor should be writing in such a way. And here you You see this kappa. Kappa is the quantum number, angular momentum quantum number. In Dirac terminology, it is a combination of the orbit angular momentum L and the total angular momentum G. So it's a combination of L and G. And then you see this up and low components. So you will see this is up components, and this is the kappa, that's ARM. And this is angular momentum of angular part, that's LGM. And then be careful about this low components. You will see for this low components, you will see this, their total angular momentum are the same, that's O is J, but the orbit angular momentum is a little bit different, right? This orbit angular momentum you see for the low part, this is L tilted. This L tilted, their relation with L is just like this one. So immediately from this Dirac equation, this mysterious pseudo spin or should be the angular momentum, you can immediately find that is related to the pseudo spin symmetry. By the way, it's surprising, right? Because Dirac equation existing already 100 years. But nobody has checked carefully how the Dirac equation looks like. I will tell you later, because we also found something missing in the Dirac equation. And then you see, after you put in here, then you end up with this Dirac equation, this radial Dirac equation. This radial Dirac equation simply is the Kappa differential equation. This Kappa Dirac differential equation, if you simply pick up one numerical calculation textbook, this is a very classical example how to solve this equation, right? How to solve this equation. So you can always find the solution there. And then similarly, this Klein-Gordon equation, if you have the Meson field, then you can use Green function to solve these equations. Okay, then I will tell you how to solve these equations, because Yao-Chen has already told you. This is Dirac equation, right? This is radial Dirac equation. And here we have this so-called the vector and scalar potential. If we plotting in such a way, this delta means vector potential minus scalar potential. Because this is positive, this is negative, this is big quantity. And sigma is V plus S. V is positive, S is negative. So this is attractive, right? Anyhow, this is the potential for these equations. And then in order to solve that, how to do that? Numerically, they are so-called we just show how the potential looks like. So this, for example, this is V plus S for 928. This is for a proton. This is for the neutron. After we solve this equation, finally we can get the self-potential look like this, right? But then we assume this is something we guess. And then you say this is a neutron potential. Normally, why for the stable nuclear we have more neutron than proton? Because the neutron potential is deeper. So we can host more neutron than protons. And then because of Coulomb potential, be careful. You see, for the neutron potential, it disappears when you're far away from the center. Their potential disappears. But for the proton, because the Coulomb potential is non-range, so you will see this is how the proton potential is much bigger than 0. For example, in 928, this Coulomb barrier could be high as 10 MeV. Therefore, you can imagine that when we're talking about the neutron halo, because neutron could be weakly bound, even the separation energy, is smaller than 1 MeV, it could be weakly bound. For the proton, be careful about weakly bending, because even the bending energy is 0, but they're still within 10 MeV bound because the existing of the Coulomb barrier. So if you go into the literature, people talking about quite a lot about neutron halo. But when the people talking about proton halo, they must be very careful. So this is the potential, scalar potential plus vector potential, and is attractive. And then this is the vector potential minus the scalar potential. This one is, repulsive, about 700 MeV. Quite big, right? This is the reason why we see, okay, if you're talking about the system could be treated in non-relativistic way because you already adopted the non-relativistic language. If you adopted the relativistic language, you see you have such a big potential, which is not so small when you're compared with that mass. So you see we have this potential already. So in this Dirac equation, you see this delta and this sigma, this potential is already known. So this is simply a normal coupled differential equation. So how to solve that? You will see you can easily use a shooting method. What is a shooting method? That means you studied from the origin to integrate it outside with a fourth order longitudinal algorithm. And then you can also integrate it from infinite inward. Then you match the wave function at some point, right? How to match them is very simple. So if you choose, for example, for net 08, we search the solution one by one. First of all, we search the solution for 1s1/2 orbiter. This is the lowest single particle level. And then you see we assumed this is single particle energy is not necessarily correct. Because if you're looking at this wave function, you will see what is not known. What we don't know is that, for example, we don't know the bending energy G here. That is one thing we don't know. Another thing is that we don't know the wave function and the origin. That's second we don't know. The third one is that we don't know the wave function and the infinity. So we have 3 unknown properties. But we have 2 equations, right? We should search for the third equation. The third equation is a normalization condition. So put that 3 conditions together, then that's enough to find the solution. So we tentatively give some energy, integrated the wave function towards. And then we have a large component and small components. We can put the large components match with each other. Then the small components don't match. There is a difference here. We use this difference to modify this energy. Then we go to the next iteration. So you see that's the first iteration. This is the first iteration. The large component look much better. And then the difference between the no components, it becomes smaller. And also the energy becomes 1.8 MeV, should be modified. And if you go to the 6th iteration, you will see the upper components, we ask them to match. The small component difference smaller. And then this is the energy. It's already very also changes. And then after the 10th iteration, you could see the wave function is always smoothed, right? It's almost smoothed. So that is how they give one quantum number, search for the solution of a single particle, and then finally you can get the wave function and also the bending energy, right? Oh, okay, just 1 minute. Then we can repeat this process. We can repeat this process. For example, for this is for 9208, this is for proton, and this is for neutron, this experimental value, and then we can get all the solutions, all the single particle level for all the system. And then after you got this system, you get the solution, you can compare with data, right? So be careful, all of this quantity are simply prediction. They are not concerned because we concern the wave function with the functional only by bending energy and radius. So now we can predict the single particle level. And then we can compare it with that data. And then after we got this, there are a lot of things we could do, right? So we'll do that tomorrow. Okay, so thank you very much. Any question or yeah, please. Very good question. Very good question. They use some knocking out and reaction. For example, you put in one proton, and then you knock out another proton. You find the energy, and then to see how this how much energy you need to remove these protons, and then you do several of this reaction. Then they have they could so to say compared with the data. Isn't that is very complicated, and even if you see the data is not a sharp peak, but anyhow that there is some bumping there. This is so to say the peak position that we can take and compare with the data. You are fully right. There are also different things to compare with the data, because you see that when you move away one proton, you get the energy, and then if you remove another one again, if during this process, the nucleus has memory. The man already then lose the one nucleus, so this measurement could be different. So sometimes when you do this comparison, you must be very careful. Make sure that what we calculated could be compared with them. Yeah. Any other question? So if not, then maybe we continue tomorrow. Thank you very much.